Okay, here we go. Lecture 5, round 2 for me, round 1 for you guys. I do have a new camera. It's a little bit off-putting. Everything seems in a slightly different location. It's also a fisheye lens, which is never flattering.
No, that's just how you look.
But I'm going to roll with it. I was hoping I could just turn the camera down and you guys could see the calculations. Still gonna have to stop and start, and I'll do all the calculations separately. It's just that the conversation flows a little bit better. You guys can still kind of scrub, like rewind and go backwards, but I wasn't able. It's still, I can't prop it up. I need something to sit it on, and it wasn't working. So. But it is a lot better that I will be able to make it one continuous video that I upload for you guys. It makes it a little bit cleaner, more organized. Some people have gone out of the way to email me to say that they don't mind. You guys haven't had that many calculations. It's been more the undergrads, and I do appreciate those emails. It is also a little bit easier for me to maintain and kind of keep track and not lose something by having it all in one video right away after I film it, that I can kind of do it all in one complete thing to upload for you. With 3 courses, with some of them having multiple examples, I was uploading like 15 videos or something like that. So this helps me just not screw up, really. So you guys are going to be jumping into the math today. This week and next week, not too bad. I'm going to ease you into it. The last few weeks are math heavy. I have tried to work it out that less of your assignments are weighted because with those heavy math ones. The last 2 weeks are probably the hardest math section, and they're not those aren't marked assignments for you guys. I will give you assignments that you guys can work on and treat them as if they were assignments. You can even submit the answers. I'll even allow it to show you the right answers right away, but I'm actually going to give you the answer sheet so that you can go through, do it, but then when you're ready, go check the answers, and that's for the last 2 weeks. You will need to know some of that for the exam, though. They really are kind of the culmination of the entire course, and we have no answers until the end of the last week. Even then, we only have answers for 1/2 of our strength equation. Remember, we need our reduced capacity to be greater than our factored load. And by the end of this course, we'll be able to calculate our entire factored loads. Next term, we will figure out the reduced capacity. So technically, we won't have any final answers until the end of structures 2. So this week, we're going to actually start talking about loads. So these are all the loads that happen on our building. We're going to do it in 2 parts because there's enough of it. This is probably the harder week where we have a little bit more information coming at you, and we'll do some math examples. Obviously, the questions that you guys will have on your assignment are harder than the ones you'll end up with on your exam. The assignment is the place to make it seem the hardest. So don't get too overwhelmed. You will find that the exam is probably a step down in difficulty than the assignments. All of the content will be on there, but the whole point of the assignment is that it is the harder part, where you have the time and luxury to reach out to your TAs, check alternate examples, go back and look at your books, write it out 2 or 3 times, talk to your peers and say, hey, how did you work through this one? I tried it this way. You guys are allowed to communicate. You guys would normally be kind of sitting in things coming from my computer. You would be normally kind of sitting, doing part of this at the end of your tutorial, or kind of sitting in your studio space working on this. So the assumption isn't that you are not allowed to talk to each other. In fact, I want you to talk to each other. I want you to be reaching out to each other and helping each other through these. So before we talk about these loads, we often talk about them in terms of kPa. And that's a unit of measurement where we have kilonewtons per meter squared. And let's just kind of help quantify what that means for us. We're going to talk about different loads today. We're going to talk about dead loads, live loads, snow loads, wind loads, and earthquake today. Next week, we'll move on to temperature, soil, a little bit on pre-stress. Those are just kind of the lower ones. And then we'll talk about how we combine these loads. Remember I said that in that factored side of the equation, we don't weight all of the loads the same. The weight of the table, if Shannon gets on the table and we design that table to hold Shannon, and then Shannon goes out and eats a cheeseburger and comes back, the variability in the weight of the table doesn't actually change that much. The variability of Shannon, does she eat a junior bacon cheeseburger, or does she eat the double quarter pounder with cheese, a side of fries, a large Coke, and an apple pie for dessert? So there's more variability in the live loads and the kind of the loads that we're estimating or using scientific research to figure out than the dead load, because we don't want more dead load because that's more expensive. Why would we waste our money building it bigger than we need to? So we don't weight the loads the same, and that's what we're going to talk about next week quite a bit. Let's look at what kPa means. We often talk about these in kPa, which is just another name for saying kilonewtons per meter squared. Normally in this course, I would put a big tape square on the floor that is 1 meter by 1 meter. Obviously, we're not going to be doing that, but I'll show you where that would come in later. So what does 1 kilonewton mean? Before we can even talk about 1 kPa, what does 1 kilonewton mean? And I think I touched on some of this earlier in the term, where I have 3 courses going and bits of them are all in it, and I've rearranged the order of 2 of the courses. I kind of forget little tiny bits of what I've said to who. So there's no problem in just reminding ourselves, what does 1 kilonewton mean? I looked up Channing Tatum to see how much he weighs. Dude's only like 180. I was really surprised. So we're going to stick with Arnold because I looked up The Rock. That dude's massive. I couldn't find anyone else that was around 225 pounds. Why are you laughing?
I'm close to 225. You could use me.
Arnold, kind of in his heyday, was around 200. I think he was 229 pounds, but he's around 225 pounds, which is, if you do the conversion, pretty darn close to 1 kilonewton. I think it's like 224 point something, but 225, pretty darn close, 1 kilonewton. So Arnold is about 1 kilonewton. I hate using a model, but it's actually hard to find people that you can find a picture of someone at half of a kilonewton. Me back in the day was, but nobody wants to see a picture of me in high school. I was a total nerd. You don't want to see that. So we're going to use famous model lady, who actually, thankfully, is heavier than most of the models for her size. So kudos to that. I say let's support that. But this lovely lady is about half of a kilonewton. Me and a couple of my hockey pals, add up some weight there. We're around 2.44 kilonewtons. So kind of just to give you a sense of how, it's switching to even kilograms, if you're used to talking in pounds, is a little bit of a throw off. Switching to kilonewtons is probably even harder. For those people who are from England, I'm sorry, you talk in stones. Nobody knows what you guys are talking about. So what does 1 kPa then mean? Well, kPa is kilonewtons per meter squared. So 1 kPa is saying that we have 1 kilonewton in a 1 meter by 1 meter square. So we take that 1 kilonewton weight and we put it on our 1 meter by 1 meter zone. Now, this is a point load in that 1 meter by 1 meter square. What we're kind of really saying is, imagine we take Arnold and we turn him into silly putty and we squash him and spread him evenly over that 1 kilonewton by 1 kilonewton. But this is just to help illustrate kind of what we're talking about there. Are you laughing at me? I just can't. You haven't ever heard all of my lectures.
I know, I've got to get Jeff Rosati to do Arnold squashed down into one.
Yeah, that's actually probably not a bad image to have.
Photoshop.
So 1 kPa would be, or sort of half a kPa would be model lady in that 1 meter by 1 meter zone. So half of the load on the same area gives us half of the pressure, half of the kPa. If we wanted the full 1 kPa, 2 of her would be squashed in that little area. So that's just to kind of help you talk about things. There will be some things over kind of the next couple courses that I might refer to things in Arnold's just to kind of help you get your head around what that means. So live loads vary depending on what our building is and where in the building we are. What's really nice about this is that you can open up a book and there is a chart that tells you if you have this building, this is what the live load you use is. You guys have access to that chart. It has been uploaded. It's in the downloads section. It's also in this week's module. So you have access to the live load charts. I'll show, I've just pulled kind of some of the key ones out for this. So an assembly area is kind of our large load, are a bunch of people kind of gathered in a space, and it is 4.8 kPa. For those of you that are old school, 100 pounds a square foot is often how you'll hear it referred to. So 4.8 kPa, 4.8 Arnolds jammed into that 1 meter by 1 meter square. That is a whole lot of oiled up person in one tiny little space. If we were talking about model lady, we need 9.6 of her to equal 4.8 kPa. That's a lot. This is often where I would say to the class, okay, I need 4 other people to come stand in the 1 meter by 1 meter square that I had taped on the floor with me. And we'd all kind of gather in there. And then I would point out that probably none of us in that were actually, 225 pounds. That might be a couple people in the class. Most of us range somewhere over that zone from half a kPa to probably, or half a kilonewton, even up to 2 kilonewtons. So this is kind of an average. So I said, all right, 2 more people come join us in the square. And we're probably getting pretty close to 4.8 kPa. It was always uncomfortable before. Times of COVID, it would be terrible. We'd actually be breaking some laws. We'd be pretty close to breaking some laws there. So you can imagine that is not a comfortable state to be in. 4.8 kPa, you are highly aware when you are in a 4.8 loading situation. But it happens. Anyone who's back before COVID was on a subway platform, you would have experienced 4.8 kPa. So it is something we do see. It's not an unrealistic loading case, but it's not happening all the time.
Sorry, I just realized that COVID loading is about 0.5 kPa.
Yeah.
So one person every 2 by 2
every
square
2 by
meters.
2 square meters.
So that's every 4 square meters.
So COVID loading much reduced. It'll be interesting to see kind of if this persists. It won't change. It would be hard to kind of roll the clock back on these loadings. 4.8 kPa is probably going to stick around. So 4.8 kPa, we do see it. In a building that we designed for 4.8 kPa, we probably don't have 4.8 kPa everywhere all the time. We're going to talk about that in a little bit. So, bleachers, stadiums, grandstands, easy to imagine 4.8 kPa. I meant to grab a picture of downtown Toronto post Raptors win, where it was just absolutely bonkers. And probably almost every square inch of downtown Toronto was 4.8 kPa. An assembly area that has fixed seating in it not counting stadiums, because stadiums, craziness happens in stadiums. It's like people lose their freaking minds in stadiums. But places with fixed seating, you don't have to use the 4.8 kPa. The chairs are in the way. You might get a person on it. You might even get people standing on the chairs. But there's objects in the way that makes it hard to have that condensed kind of loading all together. Dave, we can see you. We just about see you. I would love some water and a coffee. You'd be a doll. In a few minutes. Okay. Yes, take a phone call. Assembly with fixed seating, we can still have 2.4 kPa, but that would be, if we were actually having this class where we were supposed to, which would be in the main hall at Daniels, that would be 2.4 kPa on the upper bits. Lower bits, not fixed seating. They can move around. We know they clear them out and have parties in there. That would be 4.8 kPa. Dining halls, if they're under 100 square meters, 2.4 kPa. Over 100 square meters, 4.8 kPa. And why the difference? Well, if you've ever been to a wedding event in a place like that, you know that as soon as dinner is served, they clear out all the tables and it turns into a dance floor where you would definitely get your 4.8 kPa. So now we can move into some of the non-assembly loads. An office building would be 2.4 kPa in the upper floors because you rarely would have a party. You might have a party, but it's not going to be a crazy bash kind of party where you have people jammed in quite so tight. The ground floor, though, would always be 4.8 kPa. And I kind of like this illustration of it, mostly because you can see that this is usually the big grand space. In fact, most buildings will rent out their ground floor, even if it's their office buildings for parties. I know Dave's office at 134 Peter, the ground floor has those big, beautiful delta frames in the 4-story space, and that's often rented out for parties. So why would that 4.8 kPa matter? It's the ground floor. Nothing is below you. And that would make sense if we had a normal kind of foundation and that was grade and there was no basement. But not only do we often have basements, in downtown Toronto, if this is your property line, we often have setbacks for the building, but not for the basement. So often our basements are bigger footprint than the building itself, or we're connected to the path and it's just basement connected to basement connected to basement. So this 4.8 kPa has a really big impact on this zone of design right here. Residential live loads. When I first started teaching this course, it was 1.9 kPa in the majority of the house and 1.4 kPa in the bedroom. I don't know what happened in what bedroom to make them up the live load in the bedrooms, but it is now uniformly 1.9 kPa in all of the house. Vehicle loading. People are always surprised that a regular vehicle loading is 2.4 kPa. Live load assemblies is 4.8 kPa. How can that be possible? Well, cars, as much as they're very, very heavy, they're actually spread out over a pretty large area. Now, I'm sure there's one or two of you saying, hold up, Shannon, that load actually comes down on a tiny little zone of 4 spots where we have our tires. And you're right, that would be the impact on the surface of that object. And we'd have to worry about local punching shear for concrete, for example. But the load for the building floor itself would only be 2.4 kPa. So if you take the weight of any vehicle and kind of divide it by its perimeter, you would find that we're below 2.4 kPa. That starts to change if we're talking about heavier vehicles. So buses, light trucks, and then big trucks. And this one's really important because it has impacts throughout the rest of our kind of design process, is 12 kPa. And that has an impact on driveways, sidewalks areas, and basements. Because in our buildings, if we have basements with a laneway right beside it, we can have a truck come along that space, and it could be 12 kPa of load. And anyone who's ever dug a hole in the sand and had an annoying sibling stand on the side of it, you know that it wants to push the sand in the hole. So having, knowing that the load outside the building can be quite heavy can have an impact on how we design that foundation wall. And we're going to talk about that later in the, did we already talk about that? No, we're going to talk about that later. Now, this always throws people off, and I'm honestly a little bit shocked why it throws people off, so I'm going to try to kind of really talk through the philosophy behind it. If you're designing a floor and its live load is 4.8 kPa, obviously that whole zone could be filled with 4.8 kPa, no problem. The bigger and bigger the area you're designing, this doesn't change the tributary area for any necessarily particular object, but the tributary area of accumulations of zones. So a column, for example, is a really good example. If it is the bottom floor column of multiple floors, the odds that all of the floors, the tributary area of all the floors it's supporting, are going to see that maximum load at the exact same time, statistically, the odds of that happening decrease. So, any given part of that being maximally loaded, pretty good odds. But the odds of all of them simultaneously being loaded goes down. So, a live load reduction factor doesn't apply to a building as a whole. It is each individual object that you're designing. You can stop and consider it. It might not have any impact on your design at all. But what we say is, if the tributary area is large, the odds of all of it being loaded fully go down. So we will say, thank you. It's my birthday, so he has to be extra nice to me today. I get to demand whatever I want, right? You're just gonna bring me like grapes and chocolate. I will be coddled all day long. I got to sleep in until 5:30 this morning. It was glorious. So the odds of all of that area being fully loaded to that maximum and comfortable load simultaneously goes down. And we will, in a minute, go through a calculation of that. So different elements, different live load reduction factors. In fact, a column in a building, as it goes down the building, its tributary area increases because it's picking up, this tributary area from this floor, this tributary area from this floor, this tributary area from this floor. It could have a larger live load reduction factor on the lower levels of the column than the upper levels of the column. We're going to do an example exactly of that. The example we're going to look at is live load reduction. We want to figure out the live load on this column C. I guess it's actually A1. So slide 17, we're going to change that to A1. And so we have a 7 meter by 8 meter bay, and it's this column right here that we want to check. And they've given us this information that is somehow missing the heights. So I will add that into this. It doesn't actually make a change to the calculation at all, but it's kind of nice to see. So I will kind of just give you a better, I'll even give you an image of the whole building, because I've modeled this building just so that we could have something to work with kind of going through the course if we find it helpful. And we're going to use this building probably through a couple examples throughout the project, or at the course. So this is our floor plan, and we want to look at the live load reduction factor on this column. And we've got a ground floor here, level 2, level 3, level 4, and the roof. Level 2 has 2.4 kPa, level 3 has 2.4 kPa, level 2 has 2.4 kPa, and the ground floor is 4.8 kPa. And we want to look at the column from level 4 to the roof, level 3 to level 4, level 2 to level 3, and level 1 to level 2. So we will go through and we will do that example now. Okay, we're going to take a look at our live load reduction, our live load example that includes a live load reduction factor. We have a column on a building, and we want to find out what the live load is on it at various elevations on the building. So we have it from level 3, from level 4 to the roof, level 3 to 4, 2 to 3, and then ground to 2. We have already figured out, we already know, well, we've been told this is an office building, so we need to figure out what the live loads are for it, and then we need to figure out the tributary areas, and then we need to calculate the live load reduction factors if they apply, and calculate what the load is on the column. So let's just take a look at this plan here for a second. We have 1, 2, 3, 4, 5, 6 bays of 7, so it's 35 meters long, and 1, 2, 3, 4 bays of 8 meters, so 32 meters in this direction. We're going to be looking at this column here at A1. It's not great viewing it from this, but there are columns at these interaction points. I'm going to add a better image for you guys to also just take a look at that shows the columns a little bit better. So it's a little bit easier to see kind of what we're looking at framing wise. So let's just bring that down here a little bit. Here is a long elevation of the building. Here's the short elevation of the building. They've told us the elevation of each story. And then they've asked us to look at column A1. So this column right here. Now, it's an office building, so we know that the live load should be 2.4 kPa on all of the floors. And then at the ground floor, it's 4.8 kPa. The roof, they haven't told us that it's an accessible roof, so we don't have a live load that we need to calculate there. There will be the people that go open the building code and look, and it will say that the roof needs to be designed for 1 kPa. It does not need to be included with any other load cases. So what we would be including in this would be snow on the roof, which is what would govern. So for all intents and purposes for this course, you can assume that there is no live load on the roof unless it is an accessible roof. So, you know, a party happening up there, or a rooftop kitchen, something like that. So for what we're going to be doing, you're going to assume a live load of 0, unless I tell you explicitly otherwise. So we want to figure out the live load for all of these conditions. So let's start with our calculations. Let's take a look at our roof. Let's take a look at our column going from, let's look at it from, roof to level 3. So it is supporting the roof. Live load on the roof equals 0. So the tributary and the tributary area that the column is supporting for live load is 0 meters squared. There's no tributary area that has live load on it on the roof. So that one was kind of easy. Let's look at, I'm going to start writing it differently. Let's look at, sorry, this was level 4. Let's look at level 3 to level 4 here. The live load on level 4 is 2.4 kPa, and the tributary area from live at level 4. Let's just go back to our plans here. It's this column right here, and this is our bay. So it's half of 7 meters times half of 8 meters. So 7 divided by 2 times 8 divided by 2. Let's just take a look at that. 7 divided by 2 times 8 divided by 2. We get 14 meters squared. Now, if we can apply a live load reduction factor on this. So let's take a look. We are not an assembly area. An office building is not considered an assembly area. So we can use this live load reduction factor equation here. Live load reduction factor equals 0.3 plus the square root of 9.8 divided by our tributary area. But we can only use it if our tributary area is greater than 20 meters squared. So we don't get any live load reduction factor. So our live load reduction factor here equals 1. We don't get to reduce it. The factor is 1. It has 0 impact on our design here. The column from level 2 to level 3. This is where it gets interesting. We have the live load from level 4, and we have the live load from level 3. This is 2.4 kPa, and this is 2.4 kPa. Our tributary area from live level 4 is 14 meters squared, and our tributary area for live load from level 3 also equals 14 meters squared. So our live load is the same on both stories, but our tributary area, we have twice the tributary area now. So our total tributary area equals 28 meters squared. That is greater than 20 meters squared. So we can calculate our live load reduction factor. Equals 0.3 plus the square root of 9.8 divided by 28. Let's calculate our live load reduction factor here. We've got 0.3 plus the square root of 9.8 divided by 28, or 0.8916. I'm gonna keep a few significant figures here. You could maybe drop one. Maybe you could do 0.892. I'm just gonna try to keep as many as I can right now. I've done this in Excel, and I want no rounding issues when I show you both of them. So the live load from level 2 to level 3 is 2.4 kPa times 28 meters squared, but also times our live load reduction factor. kPa is kilonewtons per meter squared, so kilonewtons per meter squared times meters squared is going to leave us with kilonewtons. Our live load from level 2 to level 3 is 2.4 times 28 times 0.8916, or 59.92 kilonewtons. You could probably say 60. I'd be okay with 60 kilonewtons, or 59.9. I'm just going to keep a few significant figures here just to kind of keep our rounding going nicely. And then let's look at level 1 to level 2. So now we're carrying level 2, level 3, level 4, and our roof. So the live load due to roof is 0, and our tributary area equals 0. Our live load for level 4, live load for level 3, load for level 2. These are all 2.4 kPa. our tributary area for each of these is 14 meters squared. Our total tributary area for live is 14 times 3, or we have 14 times 3 equals 42 meters squared. We can calculate our live load reduction factor, 0.3 plus the square root of 9.8 divided by 42. We have a bigger tributary area, so we should get more of a reduction. So let's calculate that out. We've got 0.3 times the square root of 9.8 divided by 42. Oh, sorry. We have 0.7830. So the live load from level 1 to level 2 is 2.4 kPa times our 42 meters squared times 0.7830. We calculate this, 2.4 times 42 times 0.783. We get 78.93 kilonewtons. So what I've done is I've taken these values and I've just kind of turned them into a little table for you, just so that we could take a look at these at a glance. I showed you what the cumulative tributary area is for each of these sections of column. And then I've shown you what the live load reduction factor is as we go down the building. I've shown you what the live load is without the live load reduction factor, just so you can see at a glance how it impacts it. And then the live load with the live load reduction factor. And so this would be the design live load we could make use of. So that's our live load reduction factor example. Okay, let's talk about dead loads now. Live loads, we know we're picking what type of building we're making. The owner is, and so that's telling us what our live loads are. And if we have a mechanical room in it, we'll go look up the mechanical loads. You guys have access to that sheet, and you guys will have definitely questions on your assignment where you just have to go look at a list and get information off of it. Dead loads, we're in control of. Us as the design team are picking the things that we build our building out of. And so because of that, we're in charge of the dead loads. We have two components that for you guys almost have no real meaning in them. It matters to me because of the way I model things. A lot of software breaks out the self-weight and then the superimposed load. So the self-weight is literally the weight of the individual objects in our building. That's really kind of only become a broken out component in the past few years, as our modeling software actually will, say your beam is this much and we're going to include that specific weight. Superimposed loads are the things that go on it. So that's really kind of where you come in. You guys are picking the finishes, how much concrete topping we might be putting on something, what type of roofing we're using. Those dead loads, superimposed dead loads, often come from you guys. For most purposes, we would figure out the self-weights and the superimposed loads and add them up. And so most of the things we're going to talk about now are going to be just those two things added up. Most of the common things have an assigned dead load to them because they've been built enough that we've measured them and weighed them, and we now have kind of published tables of pretty darn close to how much things weigh. People are sending me memes today, because it's my birthday. So self-weight and superimpose loads, sum them up, we get them off the tables, and we can figure out our dead loads for our buildings. What does that chart look like? Well, here it is. We can take a look. We have steel decks, so it would be metal decks. We have concrete, so an actual volume of concrete. That is not concrete on metal deck. That bad boy is over here, where look, we have 38 metal deck, 65 millimeters normal density concrete, 195 or 1.9 kPa. Plywood, wood joists, walls and cladding, floor finishes, roofing, insulation, and ceilings. So you guys have access to this. It's in the slideshow, obviously, but you also have this PDF that you can download and kind of scroll in, zoom out, so you can see it a little bit clearer. You're going to use this in the assignment as well. So now we're going to move on to some dead load examples. And I think this one, I'm not going to break off and do it on paper because we can talk through it pretty easily right here. It's probably almost easier doing it here on the slideshow because it's not really math, it's looking things up on the chart. So this says, figure out the dead load of this roof example. So we have 4-ply roofing with gravel, 6 inches of rigid glass fiber insulation, 38 metal deck, open web steel joists, some amount for our steel framing, mechanical, electrical, and a suspended load. So let's go take a look at this. We had 4-ply with gravel, 4-ply roofing with gravel. Let's look over here. Roofing, 4-ply asphalt and gravel, 0.32 kPa. The next thing we had was our 6 inches of rigid glass fiber insulation. So let's look at our insulation. Now, note this. This says per 100 millimeters thick. We have 6 inches, which is 150 millimeters. So, 150 divided by 100, we need 1.5 times whatever they give us in this list. So glass fiber rigid, 0.07 kPa. We're going to need 1.5 times that because we have 150 millimeters, not just 100. And this is telling us how much 100 millimeters weighs. 38 metal deck. So steel decks, 38 millimeters deep, up to 0.91 millimeters thick. That is normal. That is the one you guys are going to use. Don't use anything else unless I really went out of my way and said 1.22 to 1.52 millimeters thick. Stick to this. This is what we're going to use. In spite of me saying this every year, maybe it'll be different because you guys have access to the videos, but in the past, I've said this in these examples, saying it right out loud right now, and inevitably in the exam, people will pick the 0.15. And I'm always kind of baffled by it, but I've said it now. You guys are going to use the 0.1 kPa. Open web steel joists. Now, we don't know how deep they are. We don't know how often they are. We know they're probably 2 meters on center because we talked about our sizing guidelines, and we know that that's pretty normal if it's something picking up metal deck. So they're going to be at 2 meters on center. But we don't know what that value is. What we do as the engineers is we make an estimate. We figure out all the loads on the open web steel joists. We design it. And then we look up how much that one we designed weighs, and we go back and check and see if it matches our estimate. If you've been down this road enough, you know that it pretty much always matches the estimate. Ooh, parcels. We know it pretty much always matches the estimate. So that means that I'm pretty good at knowing what the rough estimate for these things is. And you know what, it's kind of industry standard. I am going to tell you what to assume. I won't make you guess that. You don't need to go do any math. I will tell you what to assume for an open web steel joist kind of weight. And what we're saying here is not how much individual open web steel joists weigh. Imagine you took all the open web steel joists, pureed them in a blender, and then spread it out like peanut butter over the floor. We're distributing that load everywhere to help us do the calculations for all of the other elements. Same thing with our steel weight. We're saying we know that there is some cumulative weight of steel in the building, and we're going to smear it out over all the floors to be able to do those calculations. So I will give you those, and I'll show you those in just a minute. Mech-elec, that's shorthand for mechanical and electrical. Obviously, specific objects would weigh more. We have a big rooftop unit. That's going to be something very specific that the mechanical engineer has to give the engineer a cut sheet for, and we'll go look up what the actual weight of that unit is. This is talking about a general allowance to kind of hang from your ceiling. So this is your lights and some ducts and vents and wiring. So kind of like the basic stuff, not the condenser units and the air conditioning units and the air handling units. That is specific objects. This is the general allowance. And so let's take a look here. Let's look in ceilings. We have a few things listed here. Well, look, ducts, pipes, wiring allowance, average condition, 0.25. So that is the standard mechanical, electrical loading allowance that we use. Oh, looks like my husband ordered lots of beer. He might need me to sign for that. Oh. He's still in the driveway, so he was able to sign for that parcel. So 0.25 kPa, loading allowance for mechanical and electrical. The last thing was I believe, a suspended ceiling. So they just said suspended. We know they're talking about a suspended ceiling. This is the standard crappy metal tees with the kind of insulation board hanging from it. You've definitely seen them in office buildings. You've probably seen it in a doctor's office. It's the standard kind of ceiling hung from your roof. So it hides all the mechanical and electrical junk. Tiled ceiling and suspension system with fixtures average. So that is our suspended ceiling, 0.2 kPa. So let's take a look at that. We had our 0.32 for our 4-ply with gravel, our 0.07 times 1.5. You could round up or round down. I will usually give you a plus minus 0.01 in an answer. So if you're out by that amount, probably no big deal. You'll still get the correct answer. So if you round it up instead of down, you wouldn't get that wrong. 38 metal deck. We know that the normal one is 0.91 millimeters, and that is 0.1 kPa. I have given you here what to assume for the open web steel joists and the steel. So 0.15 and 0.2. Mechanical electrical, 0.25, and a suspended ceiling, 0.2 kPa. We would sum all that up, and we would have a total dead roof load of 1.32 kPa. So we're saying every 1 meter by 1 meter portion of that roof weighs 1.32 kPa. So if we had a 10 meter by 10 meter roof, that would be 100 meters, we would have 132 kilonewtons, because every 1 meter by 1 meter weighed 1.32 kilonewtons, and we have 100 of those, so 132 kilonewtons, just to give you kind of context. Let's talk about what that means for the deck and what that means for the open web steel joists. Now, the deck itself is carrying the roofing and some insulation and its own self-weight, but it is sitting on the open web steel joists, and that is sitting on the steel. Now, to design the deck to include the weight of the open web steel joist is penalizing the deck for a job it's not doing. So often for the deck itself, we'll look at what components it's carrying, because it's not carrying everything in the roof. So we will say, okay, it's got the roofing and the insulation sitting on it and its own self-weight. So we'll sum up just the things that are loading the deck. We've got 0.52 kPa. The open web steel joists, well, they're supporting the roof, which means they're supporting everything that was on the roof, their own self-weight, and then mechanical, electrical, and suspended are often hung from those open web steel joists. But they are sitting on the steel. The steel is supporting the open web steel joists. So we wouldn't want to penalize them by designing them for the weight of the steel as well. So we'd break that out. And so the deck, as much as the entire roof loading would be 1.32, the deck would be designed for 0.52. The open web steel joists would be designed for 1.12. But then all of the steel roof members would be designed for 1.32, and so would the columns. Let's do the same thing, but for the floor. We'll just do it a little bit quicker now. We've got carpet, we've got 64 concrete on 38 deck. Open web steel joists and steel, we know I'll give you an allowance for, and then mechanical, electrical, and suspended. Well, these, we know that this should still be 0.25, and this should still be 0.2 kPa. These I'll give you, but we need to look up carpet and our deck system. So let's look at flooring allowances. Flooring allowances, they've got a few different flooring weights here. Carpet, they say 0.1 kPa. So that's easy. They've said carpet, we can look that up. The other thing was the concrete on metal deck. Do not try to calculate the volume of the concrete. You do not have to try to figure out how much volume of concrete there is and add it on to the steel deck. Down here, we have deck slabs. So a 38 metal deck with 65 millimeters of normal density concrete or normal density cover, 1.95 kPa. That is our standard concrete on metal deck. If 64 millimeters on 38 millimeters of metal deck is our most normal thing, then our most normal weight for that is going to be 1.95. So our carpet, 0.1 kPa, our concrete on metal deck, 1.95. Open web steel joists and steel, I'm telling you to assume 0.15 and 0.2. Mechanical, 0.25, and suspended 0.2. We already looked those up. We sum that up. Our floors are being designed for 2.85 kPa. Again, the deck is supporting itself in the concrete, nothing else, so we'd only design it for 2.05. The open web steel joists are supporting itself, the deck, the carpet, and then the mechanical, electrical, and suspended would be hung from it. So we design it for 2.65. And then our steel beams and our columns would be designed for 2.65 kPa. Let's talk about the walls. We've got 19 GWB. That is gypsum wallboard. The very first year I taught this, I had that in the exam. And even though we kind of talked about it in the class, people didn't really kind of know that that was drywall. And I was surprised that it was the engineer telling them that drywall is often called gypsum wallboard. So I'm trying to be really explicit and really clear right now that GWB is our gypsum wallboard, which is another term for drywall. We've got 38 by 89 wood studs, 4 inches of rigid glass fiber insulation. I'm gonna just clarify that on slide 24, it's gonna be glass fiber insulation. 19 millimeters of plywood and 1/2 inch of stone veneer. So let's go back and look at those elements. We had 19 millimeters of gypsum wallboard. So let's look at our wall and cladding. Gypsum wallboard per 10 millimeters. we have 19 millimeters. And so if every 10 millimeters is 0.08 kPa, we want 1.9 times that. So 1.9 times 0.08 is going to give us our gypsum wallboard weight. We had 38 by 89 wood studs. We know that the normal for that is 16 inches on center. We talked about that with our sizing, that joists and studs were typically the most common thing for them was 16 inches on center. So that's 0.05 kPa. What was next? We had our insulation, which was, I believe, just the 4 inches of glass fiber rigid, so 0.07. Let's just double check before I say that. So 0.07. Let's go back and look at plywood. They also said we had 19 millimeters of plywood. Look, plywood has its own category. 19 millimeters thick, 0.11 kPa for our plywood. And then the last thing was 1/2 inch of stone veneer. So walls and cladding. Look, stone veneer per 25 millimeters. Well, 1 inch is 25 millimeters. We only have 1/2 inch of stone veneer. So we need half of that, or 0.2 kPa. Let's zip forward here for a second. So we have our 1.9 times our 0.07 is going to give us our 0.15, or was it 0.8? We looked up our studs, which was 0.05. Our 4 inches of rigid glass fiber insulation was 0.07. Our 19 millimeters of plywood they gave us directly as 0.11. And 1/2 inch of stone veneer we knew was half of 1 inch of stone veneer. So half of 0.4 kPa, and we have 0.2 kPa. So that's a total of 0.58 kPa. Now remember, we're saying that every 1 meter by 1 meter zone of that weighs 0.58 kPa. So I'm going to draw you a little picture here. We are saying that we have, if this is a big wall here, this here is 1 meter by 1 meter, and if it is 0.58 kPa, that 1 meter by 1 meter zone weighs 0.58 kilonewtons downward. So we have a series of these 1 meter by 1 meter sections of wall, and each one weighs 0.58 kilonewtons. Or we're saying that that wall system weighs 0.58 kPa. And that's going to be important when we need to figure out the weight of the building, for example. And we're going to do an example like that in a little bit. Okay, so here that's worked out for you here if you want to go through and see that again. So I try to always give you worked out examples as well. All right, now we're going to start talking about the other loads on our buildings. So these would be often like our climatic loads. We give different importance to these things depending on what type of building is. Most of the time, your building's going to be regular. If nobody says anything to you about anything else and you don't think of the building as anything unusual, it is a regular importance building. So get that in your head. Don't change it from regular unless you have to. You wouldn't just decide to make it something else for no reason at all, because that's going to increase the cost of your building. And we don't increase the cost of buildings for no reason at all. So when wouldn't a building be normal or regular importance? Well, a high importance building is when we need to use the building after a disaster, but the building doesn't have to be in working condition after the disaster. So think of after Hurricane Katrina and everyone gathered in the sports stadium. I can't remember what sports stadium it is now. They weren't trying to play football in that stadium, although they did eventually later after they repaired it. it didn't have to function. They weren't serving ice cream and hot dogs and popcorn, but people needed a safe place to gather. So a high importance building is a building that we might use after a disaster. So often rec centers are a high importance building because it is very common during a disaster for people to gather there. And you can have generators to run the power. So it doesn't have to be in working condition. It needs to be having some basically shelter, providing shelter for people in a safe spot. But you're not assuming you're going to play hockey, for example. One slight change on that is I have heard that some arenas may have a design implication in them that they need to be used as a morgue. It was always kind of a funny little side note that I mentioned in the past. Slightly more dire and real in today's environment where we're experiencing COVID. You can imagine in New York and in Italy, they actually did have to use things like that as morgues. So that is the rarity though. And I don't think it has to be working at full capacity. So arenas, buildings that might have to be used after a disaster would be a high importance category. Post-disaster means your building has to basically survive the apocalypse, or pretty darn close, and it has to be in working order. Now, can you think of what buildings that might be? Well, a hospital. You want your hospital to be able to survive a disaster. Your police station, ambulance station, fire station, and communication hubs, interestingly enough. We rely so much on kind of communication, digitally, television, radio, that they are often designed as post-disaster. So little kind of brick huts will often be designed as post-disaster because they need to be functioning after a disaster. They don't just have to be standing up, they have to be able to work at their intended usage. Now, the information for these values was kind of scattered through the code, so I've assembled them into one document for you. I'm going to double check that I actually uploaded importance factors. This is the problem with having 100 different drawings and PDFs and pieces of imagery, and I can't just upload it all at once because they change from year to year, and I need to stop and think about before I post it, has it changed again? But I like to give you guys an actual PDF of this image as well. But importance factors. So, regular, 1. Don't even think about it. It has no impact on the design. I didn't even talk about low importance, mostly because it's really hard to meet the criteria of a low importance. In fact, even if something does, I will often design it as a regular importance, because if it works, it works, and I don't want to penalize the project by saying it's low importance, because it raises flags with the city, for example. I have, if things don't work, been able to rationalize, okay, well, this is actually a low importance building, and maybe the wind, we actually have to use low importance. High, for wind, snow, and seismic, we increase the load. And for post-disaster, you can see here for seismic, we actually multiply it by 1.5. Now, we've talked about ultimate limit states design, or our ULS, and this is our factored load. We're going to be using these to calculate our factored loads. We haven't added our factors yet. This isn't our factors, as much as it says factors right here. This is an importance factor. We're going to actually do the load factors next week. But down here, we have a separate category, and this is serviceability. You remember how when I told you with deflection, we have dead and live and dead and snow, or dead or live, or dead or snow or live by themselves? Well, for those values, when we're talking about deflection and we're seeing how much things actually move, we just care about damages to finishes. We don't need people. It's not a life safety event. So we actually use lower loads. And no matter if it's low, regular, high, or post-disaster, we use the same serviceability requirements. So wind, we only use 75% of the wind we would use for strength design. And for snow, we only use 0.9 of the snow we would use for our strength design. So we will need to start thinking about tracking both our ULS and our SLS values. And we'll talk about that more next week, but for now I just want you to be aware that you're tracking both of these. Okay, let's start talking about our first climatic data situation, and that would be snow load. So snow load is calculated from the code. We have an equation here for our snow load. It involves the importance factor for snow, and then here is our equation. Now, SS and SR are provided to us by the code depending on where our building is. And this is determined from working with statisticians and meteorologists for how much snow falls in those regions and what the expected 1 in 50 year storm is. So what we're saying there is the worst storm in 50 years will be that amount. But this is statistics, so you could get that same storm 2 times in 1 year. It is not saying you will only ever see this 50 years, but it is the likelihood of seeing it every 50 years. You could even exceed it. So we know that that can happen, which is why we have our factors that we include, and that's the next step. We'll talk about that next week. So we are saying that the ground snow load, so how much snow falls on the ground, the likelihood of our 1 in 50 year storm happening is going to be a certain amount. And we will look that up in the code, and we'll come to that in a second. SR is the associated rain load, and we look that up as well. So SS and SR we find in the climatic data provided to us by the building code. The associated rain load is basically saying you could have that snow there and then it could rain a little bit, and it doesn't just run right through the snow and go away, it gets stuck in the snow. So our snow gets a little bit wet. So we have a certain amount of rain kind of falling on top of that snow. And that we get from the code. All of these C values, these are all factors that we apply to our snow load depending on various conditions. So these are all about our building itself. So I'm going to go through those with you. If you find doing a little bit of calculation help is helpful, you can go to this site. I have no problem with it. Check it out. A lot of engineers use it. I'll use it sometimes to kind of just double check some stuff. So climatic snow data. The ground snow load with a 1 in 50 year probability of occurrence in a year, based on measured depths and densities for locations in Canada. So, and then SR, the rain which may fall into the snow cover, increasing its weight. So I've given you guys an upload, which is the Ontario climatic data from the National Building Code of Canada. And then I've cropped a section of it. So I've looked at Toronto. Toronto, because it's a mega city, is broken up into actually 4 categories: Etobicoke, North York, Scarborough, and Toronto City Hall. So let's come over here. The snow load in KPA for a 1 in 50 year event. We have our SR and we have our our SS and our SR. You can see that North York and Scarborough see, quite a bit more snow, 30% more snow than Toronto City Hall. And anyone who has commuted from those zones know that it's often the case that you can have a big storm happening. You can be getting a ton of snow in the outlying regions, but in the downtown core, it tends to have less snow. So let's talk about our factors then. CB is our basic snow load factor. So what we're saying is that the snow falls on the ground, and they've given us that SS value. Well, when it falls on a roof, there's a little bit of turbulence and some falls off the roof. About 20% of it falls off the roof. So we only take 80% of this for our building. Now look at this. There's a part 9 value for CB of 0.6, and I have right here on the slide, does not apply to this class. Every year for the project and for the exam, like 5 to 10 people use 0.6, and I can't understand it. It says right here, do not use this. Don't use it. It's part 9. We're designing to part 4 of the building code. 0.9 is what you don't need an engineer for, and we're talking about the engineering aspect of it. We are using 0.8 for our basic snow load factor. CW is our exposure factor. So this is saying that the wind could blow some of the snow off the roof. Now this is a hard one to use. Not that it's hard to use, because it's a 1. You're going to have it be 1. I have never done a building where I have been able to rationalize using a lower exposure factor. So it says exposed to wind on all sides. That's great. But if you read the code, it says for 1 kilometer all the way around the building. And that includes trees or other buildings. So you can imagine that in downtown Toronto, you're not going to find a building with nothing else around it for a kilometer. You have to be maybe in the prairies, you could use it. And then north of the tree line, you could probably maybe lower your wind load. But for us, it is going to be 1. Again, I don't know why, but for some reason, it's usually the same people that use 0.6 end up using 0.75 for their exposure factor. Don't do it. You're not going to use it. It is 1. Use the factor of 1. Please, maybe this year, you guys will listen to me. The slope factor. I am, except for one example in the assignment, it's probably going to be 1. What we're saying here is as you slope your roof, the snow can fall off of it. But it doesn't even start to fall off of the roof until we're at 30 degrees. So it needs to be a pretty steep pitch to get snow to start to fall off your roof. You don't need to design for any snow at all until you're up to 70%. Now, a lot of architects at this point say, this is amazing. I will make a steep slope to every building I ever design and get rid of snow on my building. Well, in Toronto, it doesn't really make that much a difference. We still have minimum loads, and designing for the snow load has almost no impact on our design. So you could go through all that trouble, but it's not going to actually improve your design. You're going to have all of this void space in your roof. You've got more zone to heat. So it's not that practical. Where it might be helpful is in a spot where snow loads are ridiculously high. Northern Quebec might be a good spot to look at steep roofs. Northern BC or in mountainous regions might be a good spot to include that or pitch your roof. You can actually see that style come up in spots where it's advantageous. So like the Northern Alps, the style of construction, you might be seeing A-frame style construction. Moscow, Russia, where they have higher snow load values because they're actually much more north than us. They have that kind of onion dome shape to shed the snow load off of the roofs. Here, not that much of an advantage. I'm not saying don't make a sloped roof, but don't do it to save the world by getting rid of your snow loads. It's not going to have that much of an impact. You will have one on the assignment where it's going to be somewhere between 30 and 70 degrees, and you have to figure out what factor you could use. It varies linearly between those two. So at 30 degrees, the factor is 1. At 70 degrees, the factor is 0. At, say, 50 degrees, which is halfway between 30 and 70, it would be 0.5. Your factor would be 0.5. That might be literally the example that you have to do in the assignment. I'm not saying I would just give away the answer. I wouldn't be so crazy. I wouldn't do that, would I? Yes, I would. It's going to be 0.5. Now, the last one is the accumulation factor. Way beyond this course for you guys to calculate it, but it is super important for you to understand that it exists. So the accumulation factor is saying, and you guys have all seen it, if you have a building that is lower beside another building, you're going to get snow pile up there. If you have a mechanical unit on your roof, you're going to get snow pile up there. If you have a parapet on your roof, you're going to get snow pile up around that parapet. It's actually like a series. This isn't even the limit of that calculation. It's pretty, there's multiple steps to it. We often have spreadsheets to help us design it because it's kind of a series of process to it. So you guys aren't going to have to worry about that. You're not going to have accumulation, which means your factor is 1. It does not mean your factor is 0. That would mean you have no snow load. We're not saying you don't have snow load. We're saying you don't have this extra bit of snow load. And I'll show you what I'm talking about. So if this is your building, if this is the building we're talking about, we've got a higher building here, we've got a mechanical unit, and we've got a parapet. This is our basic snow load. There is still snow on that roof, and that is the value you guys are going to calculate. I'm not going to make you worry about accumulations. But this is what we're talking about with accumulations, that we get an extra bit because it's a low roof beside a high roof. We get an extra bit because it's around an obstruction, and we get an extra bit because it's alongside a parapet. So now we're going to do an example, and like I said, this is building off of the same building that we looked at live load with and dead load with. We have, this is even the wrong value of the building. My values are screwing up. So you guys are going to see a slightly different question here, and when I do the math, you will have that one as well. The dimensions are... I'm going to include images of the building for you guys so you can kind of just see what we're talking about. And we're going to figure out what the snow load on the roof is, and we're going to look at the ultimate limit state's value for the importance factor, and we're going to look at the serviceability case importance factor. And then we're going to calculate, just for fun, we're going to look and see what would happen if it was actually a high importance building. And then we're going to look at what the total load on the roof is in kilonewtons. It's not a calculation we normally do, but I just want to give you a sense of what the total value of snow load is that falls on our roof. So we're going to do that. We're going to do this calculation now. Okay, let's take a look at our snow example. We have our same building. They've told us that it's a regular importance building. Kind of makes sense. It's an office building. And it is 35 meters by 32 meters. We looked at that. We saw the plans for this building. It's 13.8 meters tall. It doesn't seem like it's going to have a big impact on our snow load calculation. They want us to find the snow loading on the roof using for strength and for serviceability. And then we want to know, what would that be? What if it happened to be a high importance? And then they've asked us to calculate the entire snow load on the building. Not a thing we would normally do, but it's just to help give us some context here. So we know that our snow load equation equals our importance factor for snow times our SS times our CB times our CS times our CW times our CA plus our SR. Pay attention to your brackets here. This tends to be a real way people make mistakes. So double check and remember your order of operations. You multiply these, then you multiply it by that, then you add that, then you multiply it by your importance factor. We can look up our importance factor for snow, for ULS, for a regular importance building, it's 1. And for our serviceability, it's 0.9. So when we do our serviceability calculation, we get to reduce the snow load we're looking at. So they've said it's in Toronto. We can go and look up our SS and our SR. Let's maybe go back a few slides. Here we go. we have for Toronto, Toronto City Hall, we have, if we come along here, we have SS is 0.9 and SR is 0.4. So we can, let me just bring back our calculation here. So they've given us, based on the fact that we're in Toronto, 0.9 kPa for SS and 0.4 for SR. CB is a factor that depends on the fact that the snow is falling on the roof and not on the ground. Now, if this was a really, really, really large roof, like think a big factory or something like that, that CB can start to be bigger than 0.8 because it gets big enough that none of the snow is kind of falling off the roof. But for most of the buildings we're talking about, CB is going to be 0.8, and that's pretty darn normal. Do not use 0.6, which is part 9 of the building code. CS is our slope factor. So if our roof is sloped, we would get, if it was sloped a certain amount, we would get to assume some of the snow was sliding off our roof. This is a flat building. We've looked at the drawings. We've seen that it's a flat roofed building. So we do not get to assume any of the snow slides off the roof. CW is our wind exposure factor. Remember, we only get to make any changes to that if there is nothing around the building for a kilometer in all directions. That seems pretty dang impossible to ever achieve. So for us, it is always going to be 1. And in fact, only a handful of times has that ever not been 1, even for me in what I've been designing. CA is our accumulation factor. Definitely there's accumulations on roofs. If you've got a mechanical unit up there, you've got accumulation on your roof. But it's localized, and that is way beyond the scope of this course, so I'm telling you we're just talking about the overall snow load, and we're not going to worry about that right now. So, our snow load for strength is going to be 1.0 times 0.9 times 0.8 times 1 times 1 times 1 plus 0.4. We can multiply all that out. I know this answer because I do it so often. We get 1.12 kPa. So that would be the design snow load. So that's saying that every 1 meter by 1 meter square of our roof has 1.12 kPa of snow load on it. So it's kind of like Arnold wearing heavy clothes has laid himself over the ground over a 1 meter by 1 meter area. They actually asked us to check out what the snow load in kPa would be for our serviceability version of this. So 0.9 times 0.9 times 0.8 times 1 times 1 times 1 plus 0.4. When we calculate this, we get 1.101 kPa. Now, the other thing they asked us was, just out of curiosity, what if this was a high importance building? It's not. It's a regular importance building. This is just to take a look. The only thing that changes is that our importance factor for snow now becomes 1.15. Our importance factor for serviceability stays the same. SS, SR, CB, CS, CW, and CA all stay the same. The only thing that's changing is this right here, and it's that one number. So in this case, our snow load would be 1.15 times 0.9 times 0.8 times 1 times 1 times 1 plus 0.4 or 1.29 kPa. Our SLS value is going to stay the same. We could write that down if we wanted, but we know that it's not going to change. So this was just a kind of funny little side lark that we looked at. They then asked us total snow in kilonewtons for our regular building. So what is the entirety of the snow load on this building? Well, we've calculated that our snow load equals 1.12 kPa. The roof area equals 35 meters times 32 meters. Let's take a look at that. 35 times 32 equals 1,120 meters squared. So our let's still call it our snow load, but we'll just make sure to write that it's in kilonewtons here. It's going to be 1.12 kPa times 1,120 meters squared. kPa is kilonewtons per meter squared, so we're going to be left with something in kilonewtons. So 1.12 times 1,120, or we're going to end up with 1,254.4 kilonewtons. Or it's like we have 1,254 Arnolds laying all over the roof, and that's the equivalent of the snow load on this building. We can just take a look at that here. You can see that I did this calculation all the way out for us, and I calculated the snow load for strength and serviceability, and then I did it for fun, looking at it as if it was a high importance building. So you can see serviceability, it doesn't change, and that's because our importance factor doesn't change. That note right there should be changed to high importance factor. So I'll update that one little line here that this is saying at high importance factor, but you can see that the calculations carry that through. So that is our snow load example. Okay, so let's take a look at rain loads. Rain loads don't often govern for us here in Toronto, and I'm going to show you why, but why sometimes it matters. So every roof has to be designed to support a 24-hour rainfall. The idea is that even if you have scuppers and drains and whatever you have up there to drain the water off the roof, we assume that, especially at this time of year, leaves can clog that up, maybe ice clogged it up, and the water can't drain. The assumption is that after 24 hours, you would know that you had a big ass pile of water on your roof, and somebody goes up and manually cleans the drains or does something to make the water leave the roof. So we have to assume that at least a 1 in 50-year rainstorm will be standing on that roof for 24 hours. Don't worry about this and the volume of water. What's really important is to think about roof slopes. We do, even on a flat roof, what we consider a flat roof, we slope it around 2%, sometimes a bit more, but minimum of 2% to the drains. And that drain might be at the edge for the scupper or in the middle. You might have multiple roofs, you might have multiple drains on your roof, and you can slope it with the structure, you can slope it with insulation, but eventually that water slopes to a point. We think of the roof as flat, so it doesn't really have any kind of consequence on it. on us. But that volume of rain in 24 hours is falling, and it is sitting on that roof. But as you slope to drains, that water redistributes to have more amount over the drains, that clogged drain that we have to assume is there. And so I like to show this kind of diagram. So this is how we picture our roof as our flat roof, and that 24-hour total volume of rain falls on our roof. What we actually have is sloped drains. Now, I have highly exaggerated these slopes. Don't worry about that. It's just to kind of illustrate the point. The same volume is on the roof. So this volume and this volume, or we're looking at a 2D cross section of it, so this area and this area are the same area, or the same cross-sectional area. But look at how much water is right here. If we had a beam here and a beam here and a beam here, and that's our tributary width, that beam is carrying an awful lot more of that rain volume than those two would be. So it might have an impact locally on elements. Now, I'm sure there's other places that it would have a big impact. But in Toronto, snow always governs over the rainfall, except locally due to sloped roof drain, just sloping our roof to our drains. We could locally have an impact where the things under this higher volume. Now, again, this is exaggerated. It's not even this obvious. It might just govern when it's the rainfall. And think of, I don't know who was around in Toronto. I think it was in 2012. When we had a giant rainstorm, and I think our, do I have, no, I don't have it listed here. I did back in our climatic data here. So take a look at this. In Toronto, Etobicoke, North York, Scarborough, our 1 day, 1 in 50 year rainfall, it must be lunchtime for my little ones. Toronto City Hall, 97 millimeters. Etobicoke, 108 millimeters. Is our 1 in 50 year, 24-hour rainfall. In 2012, in 2 hours, Etobicoke had 127 millimeters of rain. So we annihilated that 1 in 50 year rainfall event. Now, consider the fact that we factor up our loads and we had no buildings collapse. There might have been local damage. There was definitely flooding, but we didn't have any collapse events. So we're in the midst of, the entire world climate change. So we will start to see these values change. But we didn't have a life safety event simply because we actually do factor up these loads. But these 1 in 50 year events are coming more and more often. Okay, so we looked at our rainfall. Let's talk about wind now. Wind it's a more complicated calculation, and you're gonna have to do some of it. I'm not gonna be that mean on the exam. You might have to pull some data or do a tiny quick calculation. Even on your project, I will only make you pull the climatic data for your building. Actually, I can't even remember. No, I have to give you guys project information. Project info. So you guys won't have to do, something too rigorous for wind after this assignment, but you're going to have to do it in the assignment, and I'm going to give you an example. We have a few things that we have to worry about with wind. If we have a building, when the wind's blowing like this, we have the windward side. But you know that the wind comes along and it blows over the building, and we actually get suction on that side, or the leeward wind side. We actually also have, as the wind goes across the roof, we have suction on the roof. It actually has wind uplift. We have to think about it downward, but we also have to think about the wind upward on the roof, which seems crazy, but the wind really does try to pull the roof off of the building. And then we have elements that we have to design for. And so those would have an exterior wind load and an interior wind load. So we have to think of the building as a whole. We have to think about the roof up and down. We have to think about walls with exterior and inward wind. And then we have interior elements that would also have interior wind loads on it. So there's all kinds of sequences that we have to think about for wind. We're not going to, we're not going to do this again and again and again and again. We are going to do one overall building calculation with windward and leeward values. So let's talk about the wind equation. We're looking for our wind pressure on our building. We have Q, which is our reference wind pressure. That's our 1 in 50 year wind reference pressure. I'm going to add that. I'm going to actually add the note. Q is actually 1 in 50. I made all these changes. I don't even know what's going on. It's like it didn't save. So our wind reference pressure is our 1 in 50 year wind pressure. Again, that's a 1 in 50 year storm. We see more than that, but statistically, this would be the worst storm we see every 50 years. We have our importance factor. We have our ultimate limit states, or our strength one, and our serviceability one. So we're going to want to look at both of those. And then we have our factors. Same way we did with snow. We have CE, which is the exposure factor. We have CP, which is a pressure coefficient. And we have CG, which is the gust factor. So Q is our 1 in 50 year reference wind pressure. It comes from a wind velocity. Now in the States, they do this calculation differently. They actually use a wind velocity to do their calculation. So we cannot just take American values and plug them into our code. And we use an hourly mean average, whereas they use a 5-second gust factor, I believe. So that's going to have an impact on our gust factor. So the way we do it, we eventually get to pretty darn close to the same values, but we cannot pull and make exchanges between American codes. It's a big pain in the butt because sometimes American codes are more comprehensive for the oddball things. So we're not talking about our buildings. Our buildings, we have a really good comprehensive code for our buildings and the elements in our buildings. But if we're talking about an open structure that sees wind on the bottom and the top, kind of standalone installations, unique shapes, domes, for example, the American code and the Australian codes are much better. And we're allowed to use those as a reference if our code doesn't cover something. It has to be something a reasonable engineer would do. But we can't just take the values and duplicate the calculations. We have to do conversions and understand how they got their values before we just plug them into ours. So Q, we don't actually calculate. We get to look that up in our climatic data tables. So this is the same one we looked at for snow. And we can see here Toronto City Hall, our 1 in 50 hourly pressure is 0.44. Etobicoke, same value. North York, same value. Scarborough has a slightly higher wind load than the rest of Toronto. So CE is the exposure value. Now this says, if anybody has ever read Ken Follett's Pillars of the Earth, you know that they were trying to build this massive cathedral, and as it got taller, they were having more and more trouble, and it kept falling down until they realized that the wind got higher. The wind values were higher as they got higher and higher. And they magically solved all that with no math, but they figured it out and started to build the building better because of that. We actually calculate that value. So our exposure factor is the height of our building divided by 10 times 0.2. But we use at least 0.9. If you had a building that was only 1 meter tall, you'd get a CE value that was really, really low, but we have to use at least 0.9. At around 6 meters, it's 1, and higher than that, we start to increase our CE. If we were in rough terrain, so this is saying that our building is protected from things around it. So the exact opposite of our snow one, we can lower the wind value. Do not use it. And I'll tell you why. And I used to have a photo that has disappeared and I cannot find it anywhere. We have to assume that the building beside us could be torn down. The kind of classic Toronto building is a narrow, long building and a whole bunch of them kind of connected together. There was a building on one of the streets, John maybe, where they tore down all of the other buildings like it, and this one was standing all by itself, and it had a restaurant in it. And that would have assumed that there was 10 other buildings kind of tied together with it. But we now have to assume that all of those other buildings could be torn down, because they could, and we've seen it happen. So it's really hard to assume that you get to use this rough criteria. So we will be using our CE equals H divided by 10 to the power of 0.2. When wouldn't that be enough? Well, if we're saying that the wind goes up as we get higher, if our building is perched on the side of a high cliff, well, we're already starting at a high value. So that exposure factor, is already peaking somewhere at the top of our hill. When I did Solaris building in Godric, I believe, it was perched on the side of a really high cliff. And so our CE value, kind of even before we talked about the building, was like 1.3 or something like that. Oops. Gust factor. Gust factor is often combined with CP, but we can break it out to talk about it. It's the maximum effect of the load due to the mean effect, it's the ratio of the maximum effect of the load to the mean effect of the load. I like to think about it, and the best way I can think to describe it, have you ever been standing outside and you can feel the wind, there's wind blowing, but you can see off in the distance there's a tree that's really moving around. And then that tree stops moving, and then a couple seconds later you feel the wind strongly. Well, what we're saying here is that a small object would feel that full gust over its full area. But as our area gets bigger and bigger and bigger, say all the way from that tree to me was a building, over there it's feeling that gust, and then over here a bit later it feels that gust. So the whole surface doesn't feel that gust all at once. And so we distribute that over the entire surface. So we're kind of averaging out the gust to the average wind simultaneously. So it has the short duration versus the long duration of the main wind. The fluctuation, as it, like I said, the tree moving over there, me moving, being affected by it over here. And even the motion of the building itself can be broken into it. So a lot of math, a lot of thought, to say that for building it's 2, and for not buildings it's 2.5. Yeah, I know. And we're talking tons and tons and tons of research to go into us saying 2 for buildings, 2.5 for not buildings. Now, that 2, a lot of our buildings kind of fall into a low building category, and we don't even worry about it. We combine it with our CP. So, except as provided, the gust factor CG shall be one of the following values: 2 for the building as a whole and main structural members, or 2.5 for external pressures and suctions on secondary structural members, including cladding. So our small objects, a window, would use 2.5. Our building as a whole would use 2. So CP is the pressure coefficient. There's not much to say about it, except that it varies depending on, the area of the building, and the proportion of our local size compared to our overall size. If a building is low, we combine it with CP. So here are I'm not going to even make you go through this. Here are the calculations for CP for most buildings. But if we meet this clause here for certain shapes of low buildings, we don't have to use this clause. We go on to a different clause. I've been finding lately that the low building clause used to be applicable to the majority of the buildings we were designing. And over the past 2 codes, that's gotten harder and harder to achieve. I just did a building for an architect where a house didn't meet the low building clause. Because it's not just about it being low, it's about its ratios relative to each other. And so this building was so narrow compared to its height and its length that it did not meet the low building criteria, which meant the design wind pressures were much higher. All of a sudden, plywood shear walls didn't do the trick, and we had to put steel brace frames in, and everybody was very mad. Even though I gave them the heads up very early in the project, the builder came onto the project and said, "You're crazy, I've never done anything like this, you're a horrible engineer." Obviously, it made me second guess everything. I went back and reached out to a bunch of other engineers just to say, "Hey, listen, are you finding that this is the case?" And they all unanimously said that in 2015, the building code, which came into effect last year, or kind of in anything being built this summer, we had to start using this clause. So that house was one of the first things that kind of got hit by it. And I just had to keep saying, I don't think it makes that much sense to just arbitrarily one day double the wind load. And it was double the wind load that we had to design this house for versus the last code. But the code is the code. Do I think the building's going to fall down? No. But I have to be able to say that this meets the building code. My mandate is to say that this meets the criteria set out in the building code, and the building code says we have to make it withstand these values. So for low buildings, if the height is less than or equal to 20 meters and less than the smaller plan dimension, the values of the product of the pressure coefficient and the gust factor can be combined according to this image. So we have it broken up into the regular portion of the building and an end zone. The reason we do this is that we say that if the gust is happening at the end of the building, it's going to try to make the building twist. And there's real advantage in designing that. So we don't say that the gust happens at both ends at the same time. That's not what we're doing. We actually do want to analyze the impact of the building trying to twist. So we have an end zone value here. So these arrows are showing you, are all pointed towards the building. So if we see a negative value, it means that the wind is actually blowing in the opposite direction of our arrow. So if we're talking about wind coming from this direction, so if we say this is the windward side and the wind is blowing in this direction, we have our end zone, our regular zone, and then on the leeward side, we have our regular side and our end zone and our regular zone. Don't worry about the roof. We would see that would, for a flat surface, start to kind of balance itself out just a little bit. And what we're worried about right now is the overall wind load on the building. So let's talk about something with a slope of 0 to 5 degrees. So slope to drain, pretty much. So our regular zone, which is 1, blowing in this direction, we have 0.75. So our CPCG is 0.75 on this surface. On the far side, 4, which is our regular zone on our leeward side, is minus 0.55. Well, that minus 0.55 means the arrow should actually be in the other direction. So blowing in that direction as well. So both 1 and 4 are blowing in the same direction. Our end zone, 1.15 and minus 0.8. But look, that minus 0.8, the arrow is going in this direction. So really the wind is blowing in the other direction. Both of them all 4 are blowing in the same direction. Here are some notes for that. it tells you how to calculate your end zone here. So what we needed to know was what our end zone Y was. So end zone Y should be the greater of 6 meters, or 2 times Z, where Z is the width of our end zone for the other direction. And it is 10% of the least horizontal dimension, or 40% of the height, but not less than 4% of the least horizontal dimension, or 1 meter. So a few calculations just to figure out how big that end zone is. Don't worry, in the assignment, I tell you what the end zone is. So you're not going to have to go through and do that calculation. We're going to do an example where we actually do the calculation though. We will do the example at the end. I'm going to finish talking about wind, and then we're going to do one building calculation as a whole. So let's talk about internal wind pressures. So we still have Q as our reference wind pressure. That's the same value. So the wind outside of the building has an impact on the wind inside the building. Because if you've ever been in an apartment building on a windy day, you know that the elevator shaft rattles. The things in that are being impacted by the wind outside. So it all has a trickle-down effect. So we have our same importance factors. It's the same exposure factor. We have our CPCG for external elements, and then we have CPCG for elements internally. So let's take a look at those two diagrams. Here is the external CPCG for an element. So we're talking about if we're trying to design the cladding, for example now. You can see that we range anywhere from 2.1 all the way down to about 1.75 for a CPCG. So that would be the external component of it. So that was the external elements. Here are components and cladding as well. So there's a few more. So this is for the roof. We would do the same thing. We would look for the wind uplift value on the roof, or downward force for the roof. And then we would have to, I'll come back to this calculation, we would have to combine the interior wind load. So I'm going to move those slides around a little bit. Move wind slides. I am hungry. So you can see here that our internal CP and CP and CG vary. So if it's category 1, so this is a building that basically has inoperable windows. So you can't open the windows, but a little bit of wind leaks through around the cracks. Our internal pressure would vary from 0 to minus 0.3 with a gust of 1. Category 2, you have some windows that can open. This would be most kind of normal apartment buildings. We would vary from 0.7 to negative 0.7 with a CG of 1. And then category 3 is things with large doors that probably won't be shut in a storm. So an airplane hangar, a storage garage, for example, very large openings that don't have a good seal. So the values for CP stay the same, but the gust has more of an impact on it. We're not going to do any calculations with that, but I just wanted to show you that it exists. And then there's a second component. If we have interior elements that aren't exposed to so those would be exterior elements that have an interior and an exterior side. But this is an interior element kind of all by itself. We still have to worry about kind of mechanical air pressures that we can create. So you can imagine that if we keep a vestibule under negative pressure, we would have a constant pressure on those walls. And those would be, typically we design that for 2.4 kPa. But if we had like a high power, like a lab where we have kind of high powered venting systems, that might be 0.48 kPa. And so now we're going to do our wind load example. So we have a building in Toronto, downtown Toronto. It's regular importance. It's 35 meters by 32 meters, and it's 13.8 meters tall. It's got a flat roof, so we don't have to worry about anything there. And they're saying find the windward and leeward wind load in the regular zones and the end zones in KPA. But list it including an importance factor for strength and an importance factor for serviceability. So it looks like we have windward, leeward, regular zone, end zone, and serviceability and strength. So that's a lot of different answers we have to do. And then they say, what is the total wind load in kilonewtons in each direction for both ultimate limit states and serviceability limit states? Now, in the snow load, we don't often calculate that total value. In wind load, we often do calculate that total value. And the reason we often calculate it is because we're looking at the base shear. So all of that wind blowing on the building is trying to slide the building. And that really becomes meaningful at the ground. And so we talk about it as base shear. And that becomes really handy because we often want to know what governs, seismic or wind. And sometimes they're pretty close to each other and we need to really investigate both of them. But if our seismic load is 10 times our wind load, that's probably going to be the one that we spend more time thinking about when we design. Or vice versa, maybe our wind is 10 times our seismic load. And so being able to talk about those base shears becomes very handy. Often, especially for the City of Toronto, we actually have to include it on our cover sheet of our drawing, what the wind base shear is and what the seismic base shear is. So let's go ahead and do that calculation now. All right, we're going to take a look at our wind load example. So we have the same building that we've been talking about, our regular importance office building in downtown Toronto that is 35 by 32 meters. It is 13.8 meters tall and it has a flat roof. They've asked us to find the wind pressure in the windwards and leeward zones and in the for both the regular and the end zones. They want us to list the pressure for strength and the pressure for serviceability. And then they've asked us to look at the total wind load for the building in each direction for both serviceability and strength. And this is a calculation we actually do for buildings, and we actually include it right on our drawings. I know I've said some of this twice, but it's kind of important, so I wanted to just talk about it. So let's start by looking at, how about I make it so you can see? That's a good starting point. Okay, so let's start by writing our wind load equation. Wind load is our importance factor times our climatic wind data that is provided to us, times our exposure factor, times our CP factor, and our CG factor. If this is a low building, we know CP and CG will be lumped together. So let's take a look at the fact, is this a low building? So to be a low building, H had to be less than 20 meters. Well, our height equals 13.8 meters. But there was two clauses. The other clause is our height less than 0.5 times our shortest dimension, which is W for us. Well, our height equals 13.8 and 0.5 times our W is 0.5 times 32 or 16. 13.8 is less than that. Yes, so we get to use the low building example. now all of a sudden I'm paranoid that your assignment didn't use a low building example, and I'm going to have to go back and check that. Like I said, these criteria for low buildings is new. If they've really changed it in the past little while. So what used to be just a no-brainer as a low building is not anymore. So I'm just going to write a note for myself to just kind of double check your assignment. Okay, so our example here, we do have a low building. That means we get to use that handy diagram that I showed you where it lists the CPCG values for us. So let's just go back and take a look at that diagram. So here it is right here. Oops. So let's come right here. Because I have this big right now, let's actually pull out what our CPCG values are for our end zones and our regular zones. Let's pull out CPCG. We know there's four different values that we're gonna need. We're gonna need it in the end zones for windward and leeward, and we're going to need it in the regular zones for windward and leeward. So let's look at our 1E value, or our end zone in the windward direction. We have a CPCG of 1.15. In our regular zone, we have 0.75, and in our 4E and 4, which is our end zones, or our leeward side, our end zone, and our regular zone, on our leeward side, we have minus 0.8 and minus 0.55. But that is really just saying that our wind is blowing in that direction and our wind is going in that direction. So they're both going in the same direction. So I'm not going to worry about the positive and negative too much for this, just because I know that they're all acting in the same direction. Okay, so since I've pulled those off, I'm going to come back to this and minimize that a little bit. Okay, so now we can keep going with our calculations here. We still need to figure out what our Q is. So what's our Q 1 in 50? We know that that's from the climatic data. And for Toronto, our hourly wind pressure for a 1 in 50 year event is 0.44. So our Q equals 0.44 kPa. CE is our height divided by 10 to the power of 0.2, or for us, 13.8 divided by 10 to the power of 0.2. We can plug that into our calculator, 13.8 divided by 10 to the power of 0.2, and we get 1.0665. Let's keep a few. You would not need to keep this many significant digits. You could do 1.07. I'd be totally okay with that. I'm just going to keep a few right now, just so we can kind of hold on to our numbers. The last thing we don't have is our importance factors, our ULS and our SLS importance factors. For wind, for a regular importance building, our importance factor is 1, and for serviceability, it's 0.75. So we pulled off our CPCGs. I'm just going to rewrite this just to kind of clean it up a little bit, and maybe it might make it a little bit easier for us. So we've got windward end zone. We've got our windward regular zone. We've got our leeward regular zone and our leeward end zone. CPCG we pulled off. Our windward regular zone was 0.75, 1.15, 0.55, and 0.80. They've asked us to figure out what the pressure is. So what we want to know is, what is our actual wind load? So what's our wind load in each one of these zones? So that is our, we could even write it here, IW times our Q times our CE times our CP times our CG. So we have a few different ones there. For our regular zone, we have 1.0 times 0.44 times 1.0665 times 0.75. So let's plug that in. 0.44 times 1.0665 times 0.75. We get 352 kPa. So this is in kPa. The only thing that's different here is 1.15. The only thing that's different here is 0.55. And the only thing that's different here is 0.8. So we calculate that as 0.540, 0.258, and 0.375. So that's all in kPa. So that gives us all of our wind pressures in those zones. So we have a higher pressure at the end zone than we do in the rest of the building. And we don't know how big that is. That seems like it's something important, but we've figured out our wind load pressures in all of the major spots on our calculation for the question they've asked us to look at. They've asked us to also list these values for serviceability. So basically, it's all of these times 0.75. So let's do the same thing for serviceability. So this would be our wind load for serviceability. We could even put the little ULS right here. And we've got it for our windward regular zone, our windward end zone, our leeward regular zone, and our leeward end zone. Everything is the same here, except those are all just multiplied by 0.75. So we have 0.352 times 0.75, or 0.264. 0.54 times 0.75. 0.258 times 0.75, 0.7 times 0.375, and we get 0.281. Okay, so we figured out our pressures for serviceability and strength design that we might need to do. Now, the thing it really asked us to do is to figure out what the total wind load for the building is in each direction. To figure that out, we really need to know what the end zone is. So if you guys remember, we have this zone here that really is our end zone. And we need to figure out what that dimension y is. And there were some clauses here on how to calculate y. I am not going to make you do that. I have done it in my spreadsheet and it's worked out, but I am going to tell you that the end zone is equal to 6.4 meters. You can follow my spreadsheet and do that calculation looking at these clauses if you'd like. I am not going to make you do that. So I've done it here for you. What I really want to do is talk to you about the calculations of the building as a whole. So we have our building in two directions. Let's talk about it first with the wind blowing in this direction. We have our windward end zone. We have our windward regular zone. We have our leeward end zone. I don't think I have another color. Woe is me. I'll use a pencil to represent our last color. And then we have our leeward regular zone. And we know what the CPCG, or we know what the wind load is for these. We know that this was 0.352. We know that this, that was 0.54. This is 0.352. We know that this in our end zone is 0.375, and we know that this is 0.258. All of them are going in the same direction. We know that this building is 13.8 meters tall, so there's a height associated with this. So we really now just need to know how long each of these lengths are. Well, I told you that that's 6.4 meters, and we know that the total length in this direction is 35 meters, which means that length must be 35 minus 6.4, or 28.6 meters. So the wind load in, let's call it our north-south direction. In our north-south direction equals 13.8 meters tall times, and then we have 6.4 meters times 0.375 plus 6.4 meters times 0.54 plus 0.352 times 28.6 plus 0.258 times 28.6. We can plug that all into our calculators. 6.4 times 0.375 plus 6.4 times 0.54 plus 0.352 times 28.6 plus 0.258 times 28.6, all times 13.8. It looks like maybe I made one small rounding error in here somewhere, but I get 322 kilonewtons. When I did it in Excel, I got 323. So I probably punched a decimal wrong when I was plugging this into a calculator. But that's why it's good to kind of double check these things. So in our north-south direction, the base shear of our building for ULS is 322 kilonewtons. Let's look at it in the other direction now. So let's draw our same building, but let's talk about our east-west direction now. We have an end zone pushing in that direction. On the windward side, we have an end zone going in that direction on the leeward side. Then we have our regular zone, or the majority of our building, on the windward side. And the majority of our building on the leeward side. We calculated what these wind pressures were. This was 0.54. This is 0.352. This is 0.375, and this is 0.258. We calculated those from this chart right here. We can calculate what the wind load in the east-west direction is for our ultimate limit states design, and we've got 13.8. Again, they told us that dimension, or I told you that dimension is 6.4 meters. The overall dimension here is 32 meters. So our regular zone is going to be 25.6 meters. So we have 13.8 times 6.4 times 0.54 plus 0.375. It's just a different way of writing the exact same thing. Plus our 25.6 times 0.352 plus 0.258. Big bracket to end it all. And we can calculate this all out, and we get 296.3 kilonewtons. So our base shear changes depending on what direction it is. That makes sense because there's more surface area in this direction than there is in this direction. So I think that was all for the wind calculation that we needed to do. Maybe we could just write ourselves a little note here. Our base shear for wind, north-south, equals 322 kilonewtons, and east-west equals 296 kilonewtons. And literally the building department asks you to put that on your drawings. Okay, talking about seismic loads, seismic loads have a really kind of in-depth analysis process. When I say that engineering hasn't really, or structural engineering hasn't had that many changes or developments in the past, 150 years, one of the places that's not true is seismic loads. And our research and study into how buildings behave due to seismic loads has really come a long way. And most of that has to do with our ability to analyze the problems. And how we can take the values, sorry, I just need to make sure you guys have everything you need for the experiment. Awesome. They're doing, in JK, they're doing a science experiment today. So essentially the concept behind seismic design is that depending on where you are, you're more likely to see a strong earthquake. And the dependence of that, the ground is moving, and your building is coming along for the ride with the ground. And how stiff the building is changes how much force the building sees. So you can imagine that as the ground moves, it's if it's a short, stiff little building, the building's whipping along with it. If it's tall and has some dynamic ability, as the ground moves, the building has the ability to dissipate some of that energy. Now, we don't do our analysis by saying the ground's moving around. What we do instead is convert that into, we basically pretend that the building and the ground are staying still, and that there's a force being applied to it. The way we do that is we, depending on your zone and how strong what the likelihood of the strength of the earthquake is, we relate that to a percentage of the gravity load of the building. So Toronto, for example, is 8 to 15%, depending on the type of soil and things like that. And so we take the weight of the building and multiply it by that percentage as the force moving sideways. Because we're going to talk next week a little bit about, actually I might have artfully just removed it from this. We're trying to sink down into the ground with a certain amount of weight, and that is our mass times acceleration. And the ground is trying to move with a certain acceleration, and we relate that to gravity. So if we're trying to sink down with a certain amount, the amount it's trying to whip us around, we relate to as a percentage of that. So instead of using the acceleration of us sinking into the earth, which is 9.814 meters per second squared, I believe it is, we take a percentage of that as the force that's trying to move us back and forth. And then the amount it's trying to tip us over, we take that load and distribute it up the height of the building, depending on how far away we are from the ground. All of that is actually even more complex when we get into what are the soil types, how does the load propagate through that soil type, are we assuming our building is stiff or not stiff, how does our building twist? So there's all kinds of things that make that calculation quite complex. That is way beyond this course. What I really want you to focus on is this percentage of the weight, or a percentage of the acceleration that would have normally been the force going down into the ground. So we can often, as a simple calculation, relate it to that. So we would figure out all of the loads that are trying to push down on the building into the ground as a dead load. And you could imagine that this earthquake might occur in the middle of a snowstorm, but it's not the worst case earthquake we're gonna see probably isn't gonna happen at the worst snowstorm we've ever seen. And we're gonna talk more about those probabilities next week. But we say a quarter of the snow, 1/4 of the snow might be on the roof at the time this earthquake is happening. Why don't we take live loads? Why don't we include live loads in trying to calculate our seismic loads? Well, if you guys remember the video that I showed you in the very first lecture, I believe, of the people trying to balance their load as the building moved. And the camera was stuck to the building, so it didn't look like the building was moving. It just looked like a bunch of people were moving around. It's kind of like having a glass of water. As I move it back and forth, the water moves at a different rate of the cup. And it actually starts to try to balance out the fact that the cup is trying to move. And so people, if anything, limit the seismic load on a building because they're actually trying to throw their weight in the other direction as the building's moving. But we can't depend on people being in the building. So the worst case would be an empty building with all of its weight in a snowstorm, but only like 25% of the worst snowstorm happening when this worst earthquake ever would happen. Our earthquake event is 1 in 2,500 years. So every 2,500 years is our seismic event. So we're going to do an example where we take the same building we've been using for the wind, and we're going to figure out what the total seismic load is, assuming that it's 12% of the weight. So we calculated our dead loads on the roof, we calculated our dead loads on the floors, and we figured out what the weights of the walls were, all in kPa, so we can figure out the total dead loads on the building, and then we can relate that as a percentage of the dead load to figure out our base shear. Okay, our seismic example. This is not the seismic example. Let me keep fast forwarding to the seismic example. Okay, so for the same building we've been using throughout the lecture, we're going to calculate the dead and snow loads to determine the earthquake force on the building, assuming it's a typical regular Toronto office building and it's about 12% of the weight that's going to translate to a lateral load. So it looks like we need to figure out what the gravity loads are to make this work. So so this is our quake example or our seismic example. So I'm going to just write myself a little table here. So I'm just going to keep track of things. I'm going to keep track of what the load type is and what the value is, maybe in kPa. I'm going to write myself out what the area is in meters squared, and then I'm going to figure out what the total, or what the weight load is, or the we'll call it P, or the downward force is in kilonewtons. So we have our roof dead load. Do you guys remember back when we calculated our dead loads, we looked at what the roof assembly was, and it was a metal deck that had 4-ply with gravel on it. We had some insulation, mechanical and electrical. We had some assumptions about the open web steel joists and the steel. And we calculated that our dead load was 1.32 kPa. The area for that is our 35 millimeters times our 32 millimeters, which we've already calculated in this course, in this lecture, is 1,120 meters squared. Level 4 had a dead load, and we calculated our floor loads to be 2.85 kPa. And again, the floor load, or the floor area, is 1,120 meters squared. Level 3, level 2, dead loads. And these were the exact same. All of the floors were the same. We also have our roof snow load. Now remember, we only use 1/4 of the snow load for this. Our snow load was 1.12 kPa. We only want to use 1/4 of it because it would be the statistical probability that our 1 in 50-year snowstorm would be sitting on the roof the same day we experience that 1 in 2,500-year earthquake is even more unlikely. The statistical probability of that is through the roof. So we don't assume that biggest, but it could be a normal snowstorm that had just happened. That probability seems pretty great. So we'll use 1/4 of the maximum snow load our roof would ever see. So those were all of our kind of flat surface areas. But we also know that we had walls on our building, and those had a stone veneer on them. So that means they're going to be pretty heavy. So we have some weight of the walls we have to include in that. So we need to know, we calculated that the weight of the walls was 0.58 kPa for the walls. So this is the walls dead load. But we need to figure out what the area is. Let's take a look at the wall area. We have this building here. This is 13.8 meters tall, 32 meters, and 35 meters. We have that surface, we have that surface, we have that surface, and we have that surface that all have wall loads on it. And what we're saying is that every 1 meter by 1 meter portion of wall weighs 0.58 kilonewtons. So every little one of these 1 meter by 1 meter zones weighs 0.58 kPa or 0.58 kilonewtons. So essentially what we're saying is that the wall area is the entire perimeter surface of walls. So we have 35 meters times 13.8, and we have 2 of those, plus our other side of our building, our 32 meter dimension, times our height, times 2 of those. So our total area for our walls is 35 times 13.8 times 2, plus 32 times 13.8 times 2, or 1,849.2 meters squared. We can now calculate what the load is for all of those. 1.32 times 1,120, so 1,120 times 1.32 equals 1,478. 2.85 times 1,120 is 3,192. All of these floors were the same. We had a quarter of our snow load at 0.28 times our 1,120, or 313.6. And then we had our walls, which weigh 0.58 kPa, times all of the wall in the building of 1,849, and we get 1,072.5 kilonewtons. We want to know what the total is here. So this is the total gravity load that is going to contribute to earthquake. So we have 1,478 plus 3,192 times 3 plus 313.6 plus 1,072.5. We get 12,440.1. So the weight of our building, the total dead load of our building, so that's the floors, the roof, the walls, plus a little bit of snow, is 12,400 kilonewtons, or 12,440 Arnolds. We've been told that seismic in this zone is 12% of gravity. So our seismic load is going to be 0.12 times our 12,440, 0.2 times 12,440, and we get 1,493 kilonewtons. So our base shear due to seismic is 1,493 kilonewtons. We can, so you can see though that chart worked out here. Our wind base shear for this project was 323 or 296 depending on the direction. Direction for the seismic load doesn't matter. If it's a percentage of weight, your weight doesn't change depending on what direction the seismic load is going. So you can imagine if you had a narrow, long building and the weight is the weight of it, in this direction, the long direction, you have lots of opportunity to stop that earthquake from tipping you over. But in your narrow direction, that same seismic load could have a really big impact. So that's why it's really important to compare your wind and seismic base shears and understand what they are. You could have that long, narrow building where your wind load is the worst in this direction and your seismic is the worst in this direction. It's going to be really badly impacted in that direction. So it's just helpful to take a look at what those base shears are. Like I said, I did the example out looking for it. I updated that to say in Toronto, so that you can see that if we actually did out the calculation and the percentage, you can see that this is actually 8.5%. The percentage isn't set based on the fact that it's in Toronto anymore. It's dependent on what is your soil condition, what's the period of your building, what ductility modifiers are you using. So how it moves can be dependent on, or what its spectral acceleration is can be dependent on a bunch of other factors. Where before, we used to just say Toronto is Toronto and it's about 12%. So depending on the type of building it is, we could have a much lower load. But in some conditions, we were under-designing these things, and now we need to over-design them. In fact, in northern Quebec, a lot of the masonry buildings that were built in the 40s and 50s, they've since discovered actually were very much under-designed for seismic loads. And there is a big remediation project happening through all of northern Quebec, where they are going in and modifying the building to be able to resist these seismic loads the way they now actually expect them to be impacting the building. Now, I'm not going to test you on this method, but I wanted to show you what the calculations look like for doing this if we were following the code. What we get is our spectral acceleration of the ground, or depending on, so basically how much is the ground actually accelerating. And it varies depending on the period of the thing that's on it. So the impact of how much the ground moves is actually dependent on how much the thing moves. So they have kind of a feedback loop. So if the thing can move quickly, we have a different acceleration that we use for the ground. Because we're pretending that the building is staying still and we're throwing a force at it instead. That's all way beyond this. There are people that just devote their kind of career to seismic kind of concepts. What I wanted to show you was that I just wanted to show you kind of the calculation that we go through. Now, this is a condensed quick version of it. Each one of these things has multiple calculations going into it. But what we do is we say, okay, let's pull the location. So this was a building in Niagara Falls. This isn't even, well, this actually should say Toronto here. This is actually one that I had a project that I took it and adapted it to make it Toronto. So location is actually Toronto. This is I don't know what slide. So I pulled the spectral acceleration values for Toronto, but there's then I figure out from the soils report what the site class is, which has to do with the behavior of the soil. And then I see how those same spectral accelerations actually propagate through those different types of soil materials. We then have information about our building. Basically, how likely is it to move around due to these seismic loads? And then we calculate the period of the building, actually how much it does in fact, or how long it takes to go back and forth as a period. And then we figure out our design spectral accelerations, which incorporates the site class and the location information. And then we can plot those out, and then we have all kinds of different equations with less than, equal to's, more than's, and if this, then that, until we can calculate the final value. And then we would come back in and we would figure out what our actual base shear is. So you do not have to go through this. The one comment we got in accreditation was that I didn't make you do the code version of the seismic design. I don't know any of the courses that would make the students do that, because it is, I mean, for me to do it for a building is half a day's work. I can't imagine making you guys do it when I understand the code and I've been through it a bunch of times. But I did want to at least show you what it incorporates, that, you know, we have to know information about the region, we have to know information about the soil at that particular spot, and we have to have an understanding of our building's behavior. And then all of those things can combine to figure out what actual seismic load we would put on the building. So that really sums up what we wanted to talk about today. I know it's a lot to kind of be thrown at you all at once, but the big takeaway tips here is that you should be able to figure out your live loads. You should be able to figure out your dead loads if somebody tells you what the assemblies are. You should be able to calculate snow load for your building, maybe not with the accumulations, but the basic snow load for your building. And you should have an idea on how to calculate wind and seismic. You are going to have to do one wind calculation, but I'm not going to make it that difficult for you guys to kind of get marks on that. And seismic, you should just kind of have a grasp that it is dependent on the acceleration of the ground, which is related to gravity. So we relate it as a percentage of gravity. So again, sorry about the late posting. Hopefully you guys can all hear this just fine and everything has worked out. All right, have a good week, guys.